So, hi everyone. In this demo lecture, we'll be going to discuss the binary search algorithm. And so let's start. The agenda for this binary search algorithm will going to be uh, first we'll discuss what searching in general is, and then we'll focus on the binary search part. So we'll understand first that in what possible scenarios the binary search is being used, and then we'll see how the binary search is used by seeing the pseudocode and using some examples. After that, we'll discuss the edge cases. So these are the edge cases basically we need to take care during the implementation of this algorithm. And then at last, we'll discuss the time complexity and space complexity along with the derivation. So let's start. Uh, First, we'll see that searching. So searching, basically, we have been given some data set in form of array or a list, and we need to perform some search operation. Basically, we are searching for some target, right? So first way of searching is doing a linear search, which is a brute force approach. And what we basically here do is either we start from the starting index of the array. So let's say that this is our array, right? So let's say that this is our array, and we can start from the first element and go up till we don't encounter 8, right? This is a brute force way, and this is for linear search, right? If Okay, now comes to the binary search. So what it approach it follows is the divide and conquer. So we basically so when we have given the search space, like if this is the array, the search space is these six elements, that is 1, 3, 5, 6, 8, and 10, right? This is the search space. So in binary search, we basically divide our search space uh, in two parts, and then we eliminate one part. We eliminate one part. Eliminate one part, right? And in ternary search, we divide the search space into three parts, right? In binary, we divide it into two parts, and in linear, we just have the single search space, right? So this is all about searching, right? Now we'll specifically see that how the binary search works, right? How we divide the element in two parts, and then how we eliminate uh, the part which is not required, right? So this is about binary search. So binary search is an optimized solution for the linear search. So in linear search, we have to cover all the sample space, but when we say we are doing binary search, we are eliminating sample spaces. We are dividing into two parts and eliminating it. So we are basically optimized here when we use the binary search. But there is a condition, right? It can be only applied to array or list which have the special property. What this special property is, so this special property says that the array should either be increasing or it should be decreasing. It should follow this monotonic behavior. So it should have this property, right? Now let's discuss this property in detail first before moving on to how the binary search is applied. We'll discuss the property on which the binary search is applied, because this is very important. So we need to first uh, find out if in a problem statement that whether we can apply binary search or not. So for that, we need to first understand on what property it is applied, right? So we'll focus on the property part right now. Okay. So coming here, we have in the screen you can see couple of graphs, which is like monotonic increasing, monotonic decreasing, and then we have non-monotonic, right? So let's say we have this sample space, which is given, and the elements in this array are 1, 2, 3, 3, 6, and 8. So if we plot a graph, it would be something like this, right? So in this, which is basically, this is, we can say this is non-decreasing, right? This is non-decreasing array. Its value is never decreased when we go forward, right? So this is monotonic. It is showing only one property, that it is not decreasing throughout the sample space, right? Similarly, we can take this example, which is the non-increasing array. We can say it as non-increasing array, right? The values are never increased when we go from left to right. That is like 9, then value is decreased, it remained constant, then it decreased, and then it decreased. So it is basically non-decreasing array, and it is following the property throughout, right? Monotonic basically. So whenever we have this monotonic behavior in an array or a list, then at that place we can definitely apply binary search. At that place, binary search we can apply. And what will happen? Our search operations will be optimized, right? Our search operation will be optimized. So these are the condition where we can apply binary search. And for what reason? Due to optimizing the search operations, right? So where it can't be applied, when the graph is non-monotonic, it means that, let's say if the array is this, right? Let's consider this as an array. If uh, let's consider, sorry, um, let me just erase this. Let's consider this array, right? This particular array. So is this array increasing? No. Is this array decreasing? No. It is following this the both behavior, that it is increasing at some point and then it is decreasing at some point, right? Like 1 5, and then it decreased, right, on 3, and then again on 8 it increased, then on 10 it again increased, and then 6 it decreased. So it is not following the property throughout, right? Basically it is non-monotonous. So in such type of array, we cannot apply binary search. We cannot apply binary search. So, and it graph will be something like this to understand better, right? So this is the behavior which we need in order to apply binary search, right? But why this behavior? Like why it should be monotonic is our next question, that why it should be monotonic. So the way binary search work is that, as we discussed, that it eliminates one part. So if it is following the monotonic behavior, then only we can eliminate one part, right, such that our answer don't reappear there, right? So if, let's say, if we are searching for some element, we have two part, right? We divided it by mid, let's say, and we have two parts, and we know that, uh, let's say our mid is 5. We know that all the elements on the right side is greater than 5, is greater than 5, all elements, right? And all elements on the right are less than 5. We also know that this is monotonic property, right? So if we are searching for, let's say, element 8, what we can say is that we can just neglect this left part completely, because we know that on the left part this property holds, the monotonic property holds, that every element on the left part will be less than 5, so we don't need to search this, hence we completely neglect this, right? So this is why the monotonic behavior is very important while doing the binary search, right? So either it should be non-decreasing, or either it should be non-increasing, but it should have one property only throughout the sample space. Very important, right? We need to take care of this. So now once we figure out, okay, that we have a sample space which is monotonic, right? Now, like, how do we do binary search on it, right? So let me just erase this. Now let's see how to do. We'll see how to do binary search for, and now up till here we are sure that the uh, sample space property is monotonic, right? Sample space property is monotonic property, right? So we have monotonic property. We figured out that. Now we need to apply binary search. So how we apply binary search? As I said that binary means we divided it into two parts. So we'll similarly divide it. And the how we divide it into two parts, we divide it through mid. So what we do is we take mid. So at each point we will have the some sample space, right? L to R, let's say. And what we'll say, we'll divide it by mid. And how we are calculating mid? Mid is calculated as mid equal to L plus R by 2. Right, this is the formula for mid. So what we say is we divide it into two part. Let's say L to mid and then mid plus 1 to R. Right, these two parts. And what we say, let's say we are searching for element 8. This element is 5 right now, and we are searching 8 is somewhere here, let's say, right? And here let's make this is 10. So what we say is that we'll come to this mid part and check whether it's greater than 8 or smaller than 8. So if it is smaller than 8, no need to go here. We'll say we'll not go here. Our sample space, search space will become this, right? Our sample search space will become this. So we'll again search in this particular space. So how our search space will get updated is, so now my new search space will become, let's say, earlier we calculated mid as L plus R, right? And then L plus R by 2, and then we found the mid. And so what our new search space in this condition will become? It will become mid plus 1 to R, right? We'll consider this search sample space rather than L to mid, right? We split it into two parts, that is L to mid and then mid plus 1 to R. And we'll use this one. So our next sample space will be here, our L will be mid plus 1 and our R will remain same. So for this again we'll calculate the mid. So you can see, like, as we are going, as we are progressing, each time we are dividing our sample space by 2. Sample space is being divided by 2. By 2. So basically we are reducing the sample space, right? We are reducing the sample space. So this way we are optimizing the binary search. So hope you got the point. So what we do in binary search, again I'll repeat. So we have some range, let's say L to R, some sample data space, and in this data space we need to apply binary search. So what we'll do, we'll find the midpoint of this binary of this sample space, and then we'll divide it into two parts. And based on the condition, let's say here if we want to check for element 8, we'll check whether it's increasing, decreasing, or any other condition we can apply. And if we are certain that it is not in the left part, we'll eliminate that part and then proceed again to the next part. So each time our sample space is being divided by a factor of 2. So this is how binary search works. And up till when we'll go? Up till we don't encounter a single element, right? Up till we don't encounter a single element. So keeping this in mind, let's see the pseudo algorithm for this, right? So what we say, that we want to find the target element, we have total n elements and a is the array, right? We set low is a value, we set it as 0. It is the left range of our sample space, and high is the rightmost range, that is n minus 1. So now what we say is that while low is less than equal to high, while low is less than equal to high, what we have to do, we'll find mid. So now what this condition actually means, if we see this, low is less than equal to high, right? So this condition means that why up till our elements, so low and high are the left point and the right point, right? So until we have number of elements as 1, this basically says that, right? Because low and high will be decreasing, and the number of elements in the array, basically our search space, will decrease. So what we are saying is that up till it is decreased to 1, up till our search space is decreased to 1. So while low less than high means up till our search space is reduced to 1, what we have to do, if we have a search space, what we'll do, we'll find the mid of that search space, right, using this, and then this basically boils down to low plus high by 2. We'll see in edge case that how we handle this, but we'll calculate the mid, and then we'll check if our a of mid is equal to target, then we simply reach the target, we can just return. Otherwise, if our target is less than a of mid, right, if it is smaller, then we know that we need to do the search operation. If it our target is smaller, basically let's say if the element was 5 here, this is the left space, this is the right space, and we wanted to search for element 2, right, target element 2. So this is the case, right, where the target element is less than mid. Let's say a5 is the mid value is 5. So we know that, like, since it is less than 5, it will be less than every other element on this part, on the right part, right? So in searching 2, we don't need to go to the right part, we'll just keep searching on the left part, right? So how will change the search space, how our change search space will change. So let's say earlier it was L to R, we calculated mid, right? So in this case, in this particular case, when the else when the target is less than a of mid, then how our search space will reduce, right? So what we'll do is that, okay, we don't need to search from here to here, that is mid to R. We'll say mid to R is non-searchable. Mid to R will not search this, rather we'll search L to mid minus 1, right? L to mid minus 1. So we have this low and high as a pointer. So this will point to our left search space value and the right search space value, right? So like when we neglect the right search space value, we need to update it, right? So now our new updated low is equal to L only, and our new updated high value, that is the rightmost point, is mid minus 1, right? So if this is the condition, what we'll do, we'll change our high to mid minus 1. Then our search space will become L to mid minus 1, right? Our next search space. So this is how we are reducing the search space. Otherwise, let's say if it is not less, then it will be greater, right? So if it is greater, then our search space will be low equal to mid plus 1. We'll do low, we'll update our low to mid plus 1, right? So this is very important, and I think you got the point that how we are getting to these values, like why we are updating this. This is updating because our search space is being getting updated, right? So as our search space is getting updated, we have kept this low and high pointer to get the leftmost value and rightmost value of the search space. Hence, we are updating these values, right? These are the pointers. Correct. So I hope you got like what binary search is, and what we are basically doing in the binary search. Now, let's discuss some edge cases which can occur in the binary search, right? Some edge cases um, which can occur. So first is the overflow in mid calculation, right? Overflow in the mid calculation. So what here I mean is that, let's say, so how we are calculating mid, how we are calculating mid. So mid initially is calculated as mid equal to, we are saying that L plus R by 2, right? But in some programming language, we have this, we are keeping this as a data type, right? And it will have some value, right? Let's say if we talk about C++, we have int. It will contain only 32 bits, right? Means 4 bytes it will only contain, right? So it can overflow. Let's say its value was int max, the maximum it can store, and then again we are adding the maximum. What it will do is it will have the integer overflow. Basically, we cannot accommodate the L plus R value in a int type. That it means, right? So instead of doing this, what we do is, like, we say our mid value is basically L plus R minus L by 2, right? This is how we calculate mid. The mid value in both cases is same. Like here as well, if we take the LCM, it will be 2L plus R minus L, which is L plus R by 2. And same here as well. But you got the point, right? Here what is happening is like we are adding two, let's say, extreme integers which can accommodate, then it will result in the overflow, right? So, but here we are subtracting it, so we are not adding, so there is no chance of overflow here, right? So this is one edge case which we need to take care. So and the language basically in which it will affect this edge case is the C and C++, Rust, where we have like int data type, long data type, float data type, etc. But in Java and in Python, it won't be the case of overflow because like we have big integers to store them. So that's the case. So if you're using C, C++ or Rust, we need to take care of this overflow thing, right? Otherwise, if we are using Java or Python or let's say JavaScript, then uh, the integer overflow won't happen due to the property of this language. Okay, cool. Now coming to the second point, which is the wrong loop conditions, right? So we see this binary search algorithm. Let me erase few part of it. So here we see like why we are doing this low less than high, right? What we actually meant by this. So this is like up till we don't encounter the search space as one, right? This tells that like while our search space is one, up till then we have to run this algorithm, right? So always take care of this low is less than equal to high, and the way we can remember is this like up till our search space is 1. So what will be the size of search space? It will be high minus low plus 1, right? This is the number of elements, and we want that until up till the number of elements are 1 will run this algorithm. So this is how you can understand it, like up till we have one element left we'll run the binary search algorithm. So uh, always like we'll have low less than equal to high. So we can take care of this if we are following this particular pseudocode, and then consisting of the infinite loop. So sometimes what happen is like infinite loop case. Sometimes while coding, what we do is like we forgot to update these values, right? We forget to update these values. So that thing we don't have to do like so if you forget updating it, what will happen, it will enter into a infinite loop, because let's say you are not basically if you are not updating this, the high value or the low value, we are not updating the search space, basically that means. And what binary search says that at every point we are optimizing our search space, the search space is being optimized, basically it is reduced by a factor of 2. So we are optimizing our search space, so we need to always update the high pointer and the low pointer, so we need to take care of this as well, right? And then handling duplicates value. So remember the property that it should be either non-increasing or it should be non-decreasing. So it can have like equal values as well, right? So we need to take care of this as well whenever we are solving problem. Just we need to make sure that uh, there are some extra special cases where you need to handle the equal values. So keep that in mind while applying the binary search algorithm. So these are some of the edge cases uh, which you can uh, take care of, right? Coming to the time complexity and the space complexity. So up till now we have seen that okay, when to apply binary search, what is the approach. So this is divide and conquer, and basically where we are dividing it into two parts and then eliminating one part, right? And it the binary search follows on certain uh, array properties only, that is it should have the monotonic behavior. This all we got it right. But let's see now how much effective it is from the linear search. Now let's try to see that how much effective is that, and we'll see this through the time complexity and the space complexity, right? So the time complexity, so what we said is that we have element, let's say 1 2 3 4 5 and 6, right? So in normal linear search, what we do, we'll go through all of this. So we'll have n operations, right? N operations of checks, right? N operations of check in linear. But what is happening in binary search? How many operations we basically need to do? So let's say we had n data space. So in each of the space, we are dividing it by 2, right? Up till we get 1. So this sample space will be divided by 2. So earlier our sample space was n, then we move forward, it became n by 2. Our sample space got reduced, right? Again, we move forward, it will be reduced by its half. So it will be n by 4, right? Further we go, it will become n by 8. Up till we don't encounter n by 2 raised to the power some k operation becomes 1, basically, right? We want our search space to be 1 to the target value, right? So how many operations will be required? So if you see, it is when this becomes 1. So we'll take n by 2 raised to power k equal to 1. So k is the number of operation. K is equal to number of operation. Number of operation. So n equal to, it became 2 raised to the power k. We'll take log of 2 both side. Log of 2 both side. It will become log of n base 2, and it will become log of 2 to the power k base 2, right? So property of log, it will become 1, and we'll say that our k will come forward basically, and this log 2 base 2 will become 1. So k equal to log of 2 base n. So basically at these many operations we require, basically log n operations, right? Log n operations. Hence its time complexity is equal to log n. You got the point, right? Every time our sales space was being divided by 2. So if we see this property, earlier it was n, then it became n by 2, and then became half of n by 2, that is n by 4, and then became half of n by 4, that became n by 8, and similarly up till 1. So we did this mathematical operation to find that how many operations we are actually doing, right? So we got to know that we are only doing log n operations, right? And here the base of log is 2, just to keep in mind, right? So now how it is efficient than the linear time? Let's say we have n sample space, so the linear time would be, linear time complexity would be o of big O of n, right? The brute force way, search all the elements. And in binary search, we just found out that the time complexity will be log of n. So let's take an example. Let's n equal to 2 power 8, right? Which is, we have 256 elements. So for linear time, it would take us 256 operations at most, right? But in binary search, how much it will be? It will be log of 2 raised to the power n, which is equal to 2 to the power 8. So by property of log, it becomes 8 log of 2, that becomes 1, right? So we can just complete our search in 8 operation, and here we have to do 256 operations. So you can see by logarithmic time, our operations are optimized. So this is the beauty of binary search. right? The operations are optimized so much. So the time complexity for this will be log of n base 2 big O of log n, right? Now coming to the space complexity. So how we are saying that how we are calculating the space. So there are two type. Now we saw the binary search. This is the algorithm, right? We can apply it into two ways, right? We can call recursive functions as well. We can create a function and then we can call recursively, right? Or we can do iteratively. Iteratively means using for loop or while loop. Here in the algorithm, we saw the while loop condition, right? Recursive is when we are calling the function again, right? So recursive call. So every recursive call takes some stack space, right? So in, let's say in iterative approach, which is the algorithm, we say that for each while low is less than equal to high. So for each call, how many spaces are we taking? So we are uh, defining mid, we have low, which is constant value here, and we have high, which is also, which varies, but it will have the constant space, right? This low and high. And then we have only mid. So each time we are just doing constant operation. Right. We are consuming the constant space. So here, what will be the space complexity? It will be O of 1 because we are using the constant space. But let's say in recursion, when we write recursion, let's say we had solve of L comma R and we did binary search, we find the mid and based on the conditions, let's say if it was less than, then we called solve of L comma mid minus 1, right? Otherwise, if it is greater, we call the solve of mid to R. So here we are calling the whole function, and whenever we call the whole function, it will have its own recursion stack. So each time the new function call will come. So how many time the new function call will come, right? Here we have seen, right? How many time we have to optimize the search space? It is basically the log n time. So for each recursion call, it will take its own space, and hence it will take its c constant space, and there will be, and how many recursion calls there will be? Log n recursion call, hence the space complexity in recursive approach will be c times log n, right? C is the constant here, so we can just write it as big of log n. So recursively it will be big log of n, and iteratively uh, we just have the constant, so it's just c, right? We are not making any function calls uh, or anything. We are just updating our low pointer, we are updating our high pointer, and we have this mid local variable, right? So I hope this topic was helpful and we got some insights on where we can apply binary search, what edge cases we need to take care of, and how all the other reasonings which are included. So, yeah, thank you so much